All right, today we are looking at Unit 5, Lesson 4. Again, we're out of Chapter 11 in the textbook, and this lesson is on the binomial distribution. We've got two content standards again today. The first one is use probabilities to make fair decisions, for example, drawing by lots or using a random number generator. The second one is analyze decisions and strategies using probability concepts, for example, product testing or medical testing, playing hockey goal at the end of the game. The mathematical practice we're going to focus on is number 4, model with mathematics. We're going to start off with a key concept on what a binomial experiment involves. The first point is that there is a fixed number of independent trials n. The second point is that each trial has only two possible outcomes, success or failure. Think about flipping a coin in this sense. Heads or tails. There's no other possible outcome. The third point, the probability of success is P, and it's the same in every trial, while the probability of failure, Q, is 1 minus P. So if the probability of success is 0.7, probability of failure is 0.3, and together they add up to 1. The fourth point is that the random variable x is the number of successes in n trials. However many trials you're doing, the variable is the number of successes. So example 1, binomial experiments, identifying them. Determine whether the experiment is a binomial experiment or can be reduced to a binomial experiment. If so, describe a trial, determine the random variable, and state n, p, and q. The scenario is, in a class that consists of 12 male and 13 female students, a group of 5 students is randomly chosen to see how many males are selected. So the first thing you want to think about is, are there two possible outcomes? Well, there are male students and female students. There's only two possible outcomes. There's no other possibility in it. However, these two scenarios are not independent because once you pick a male student or once you pick a female student, there's fewer of them left. So the probabilities change every single time. So the probability in a binomial distribution, the probability of success every time has to be the same. If we start at the beginning of the scenario, there's 12 males and 13 females. So there's 25 total. So 12 out of 25 is 0.48. But once you pick one of the males, there's only 11 left, and there's only 24 people left. And 11 out of 24 is not equal to 12 out of 25. So the probability changes every time you pick a person. And because of that, this is not a binomial situation, even though there were only two possible outcomes for what you are picking. Part B, this time it says a school study found that 65% of students have seen an episode of Glee. 7 students are randomly asked if they have seen an episode of Glee. So this one is a binomial experiment, because either you have seen Glee or you haven't seen Glee. The probability of seeing Glee in this scenario is 0.65. The probability of not seeing Glee, which is Q, would be 0.35. N is 7, because there are 7 people that you're going to pick. Example 1, we've got to check your progress problem. Go ahead, pause the video, read through the answers. Once you have your answer, go on to the next slide. This is a binomial experiment. The probability of success is 0.38. They've seen the movie, or they thought it was the best movie of the year. And the probability that they didn't think it was the best movie of the year would be 0.62, which is 1 minus 0.38. And it's 100 because you asked 100 people. Next, we have a key concept on how to conduct a binomial experiment. The first step in the four-step process is to describe a trial for the situation and determine the number of trials that you're going to conduct. Step 2, define what success is and calculate the probability of success and failure. Step 3, describe the random variable x. What is x? What are you measuring? What are you looking at? Step 4, design and conduct a simulation to determine the experimental probability. The goal here being that you figure out the experimental probability. So, for example 2, we're going to follow that four-step process. It says we need to conduct a binomial experiment to determine the probability of 2 fair coins, both landing on heads. Then compare the experimental and theoretical probabilities of the experiment. So, first step, what's going on? The trial is going to be tossing 2 coins. How many trials are you going to do? You're going to do 20 of them, because you're going to, that's going to be enough to kind of get a feel on what's going on. You want to pick a sort of high number. You don't want to pick like 4 trials or something. In general, when we get to, if you ever go to the AP statistics course, your trial size should be at least 30. However, they kind of break the rule here because they don't cover the law that says that you need to have at least 30 trials. The second step, success, would be both of the coins landing on heads. In order for that to happen, that happens 1/4 of the time. So that's 0.25, probability of success. So P is 0.25. Probability of failure would be 0.75, or 3/4. So Q is 3/4. Step 3, the variable x represents the number of times both coins land on heads in 20 trials. That's what you're trying to find. That's what your variable stands for. Step 4, they said to use a random number generator. You can do that on the calculator. You could just actually flip 2 coins. It's always faster to use a number generator on your calculator. When you do this, let's pull in the calculator. We're going to need to generate a random number, so we're going to go to Math, Probability, Random Integer. We need to pick a number. So we have 4 possible outcomes because we have either they both land on heads, 1 heads, 1 tails, or 1 tail, 1 head. That happens twice, or both tails. That happens once. So there's 4 possible outcomes. So basically you need 4 numbers. So you could do 1, 2, 3, 4. You could do 0, 1, 2, 3. You could do 5, 6, 7, 8. It's completely up to you. But just so that we mirror what they do in the problem, we're going to use 0 through 3. 0, 1, 2, 3. We're going to generate 20 numbers. Paste this in. And here's our list. So the first time we did a trial, we got the number 2. That, for us, over here, we're going to let 0 represent both coins landing on heads, and 1, 2, or 3 represent any other outcome. So we need to essentially count the number of zeros that we got in our list, and that's going to represent the success, and everything else is going to be the failure. So we have 1, 2, 3, 4, 5. 6, 7. So in my experiment here, I had 7 zeros. So my probability of success, which was 0.25, I had 7 events. Here, they had 6. That's fine. They're 2 different trials. It's okay to get different numbers from what we get in the video. So here, the experimental probability is 6 out of 20. On my calculator, it was 7 out of 20, which would be 0.35. Here it was 0.30. Both of those answers, whether we did my trial or the one that was in this video, they're both higher than the theoretical probability of 0.25, or 1/4. Next, we have a key concept on the binomial probability formula. This says the probability of X successes in N independent trials is, so this is a formula for expecting to find out how many successes we should have in theory, not through experimental trial. What should we have? This looks kind of confusing. Essentially what you're doing is you're just using N and X and using P and Q. This C is called a combination. There's a formula for it on your calculator, and I can show you how to use it. The probability is NCX times the success probability to the X power, the number of successes, times Q, the number of failures, to the N minus X power. So if we had 20 trials, like in the previous example, and we had 6 successes, this would be P to the 6th power and Q to the 14th power. And this would be 20 combination 6. And that's a command on the calculator. Let me show you what that looks like. Math, probability menu, right here, number 3. It's NCR. They use NCX, but it's the same thing. When you use this, before you type it, if I wanted to do 20 combination 6, you have to type the 20 first. Then you go to the math probability menu, number 3, and then type 6. And it will tell you that that is 38,760. The formula for doing this is 20 factorial, which is math probability 4. This exclamation point is called a factorial, divided by 14 factorial times 6 factorial. I did not use parentheses. I need to use parentheses around my denominator. Now you can see I get the same answer. The denominator will always be the number of successes, factorial, times the number of failures, factorial, and the numerator will always be the number of events, factorial. So 20C6 means 20 factorial over 6 factorial times 14 factorial. 20C8 would be 20 factorial over 8 factorial times 12 factorial. So, example 3. A candy company produces strawberry and vanilla flavored candy, 65% of which are strawberry on average. The production line mixes the candies randomly and packages 15 per bag. What's the probability that 7 candies in a bag are strawberry? So, N is 15. We're looking at 7 as our X. Our P is the proportions of successes, which is 0.65, and Q would be 0.35. So we're going to dump these into the formula. We have 15 combination 7, 0.65 to the 7th power, 7 successes. That means there'd be 8 failures times 0.35. You type this in the calculator, and you get 0.071. I'm going to show you that real quick. We're going to type 15 math probability, choice 3, 7. Make sure you hit the right arrow to get back on the main level, times 0.65 to the 7th power for 7 successes. Hit the right arrow, times 0.35 to the 8th power for 8 failures, and then hit enter, and we get 0.071, which was the same answer that we got here. Okay, we're going to go ahead and pause the video. We ran out of time. We'll pick up in the next video.